Today's episode is all about being able to add two or more vectors together. Okay, and let's give some scenarios for this. Let's pretend that, I don't know, let's say there's an airplane flying through the sky, and this kind of represents its speed and its direction. That's what a vector does. A vector has a magnitude and a direction. So you have an airplane flying at this speed in this direction. But there's a cross current of wind. Let's say there's a cross current of wind going at this speed and at this direction. Okay, if you don't want to think of an airplane, maybe a boat. Maybe a boat would be more appropriate. You have a boat going this direction across the stream, trying to get to the other side, but you'll have a cross current of the stream traveling in this direction. Well, we'll use this boat example. Where exactly is this boat going to go with these kind of forces acting against each other? Well, these vectors, you'll notice, they're not on a piece of graph paper. They're in what's called geometric form. They're just kind of floating in the air. We'll get into later when there's actually like graph paper to work with. But if there's no graph paper to work with, the geometric way to add these two vectors together is a method called the head to tail method. And here's how it works. I'm going to use amazing special effects. You're not going to believe these special effects here. All right, I'm going to peel this vector off, and I'm going to place it over here. Okay, I'm going to peel this vector off. Now remember what the head and the tail of a vector is. The part that has an arrow is called the tail. The part without an arrow is called the head. What I'm going to do is I'm going to line up the tail of this vector with the head of my first vector. Okay, the head of my first vector with the tail of the second, keeping the angles the same. Well, when I add this vector plus this vector, the resultant vector would be the vector that goes from the first head to the last tail. Okay, and this is my answer. This in blue here, this is called the resultant vector from adding these two together. And this is my answer. Okay? Let me strip these away now so you can just see it by itself. But when you add these two vectors together, you're left with this. You're left with a vector that kind of bends slightly to the left, and it obviously heads kind of to the north. If I have to give a degree to this, it'd be like at about 95 degrees. And you can see how this would actually, if we had a boat crossing a river in this direction, but a current was pushing it in this direction, overall it's going to increase the speed of the boat. The boat's going to go faster than it did when it started. Okay? Now, we can do this with these three as well. Now here I'm going to actually try to draw these out by hand. So if this is my first vector, now I'm going to try to copy it as best as I can. This is obviously an imperfect science here. Okay, so here I've copied this vector. Now I'm going to line up the head of this vector with the tail of my first vector. Now this one goes down a little bit, and it looks like it's slightly longer. That might have been a little bit too long. Let me cut that off a little bit. Okay, so this is meant to represent this vector. And now the last vector, I'm going to take the head of my last vector, line it up with the tail of my second vector. Now this one kind of looks like a mirror image of the first, just in the opposite direction. But it's roughly the same length. Okay, now when I add up all of these three, okay, the first plus the second plus the third, my resultant vector, now at this point I'm going to go back to the original head of my first vector and draw a vector to the tail of the third vector. Okay, and I'm going to kind of circle this so it pops out. This is my answer. Okay, the answer is, in essence, let me try to draw it off to the side so we can see it a little bit better. It would be this vector right here. This could be almost like a really fantastic collision. Imagine that a car is traveling in this direction, or maybe a football player. A football player is traveling in this direction with this force, and he gets collided with, he has one guy tackling him from his right at this force, and one guy kind of tackling him head on at this force. Well, the resultant force is he's going to be driven backwards a bit although primarily he's going to be driven to the left as well because this guy's force is so strong. Okay, so this vector plus this vector plus this vector equals this vector. We can find this using the head to tail method. Okay. All right, so this is how, right here, this is how we can add vectors just totally geographically. Notice I didn't add any numbers. There was no adding or subtracting or cosigning or signing. I mean, just graphically, we can take these and arrive at an answer. Okay, now that all being said and done, in algebra class, we like to have numbers. We like to really quantify these numbers. So let's look at some different examples now. How would we now add vectors together if they're in rectangular form? Okay, so let's look at this example right here. This example says graph u, graph v, then graph u plus v. Well, u is 2, 3. Let's go ahead and graph that. So this would be, it would start at the origin, 2, 3. So you can see my first vector here kind of goes up into quadrant 1. All right, and then vector v is 1, negative 3. So in rectangular coordinates, that'd be a 1, and then negative 1, negative 2, negative 3. Okay, so here is vector, I had vector u, here's vector v. So it's going down here to quadrant 4. You know, I can kind of predict where the resultant would be. If I could somehow kind of transform vector v over here, boy, it looks to me like if I were to add these together, it's going to fall right along the x-axis at a 0-degree angle. But let's see exactly what we get. All you have to do to adding rectangular vectors is super easy. All we're going to do is add our a values together. 2 plus 1 is equal to 3. And then we're going to add our b values together. 3 plus negative 3 is 0. And yes, it really is that easy. Adding rectangular vectors is one of the easiest things you will do. My resultant vector would be, let me do this one in a slightly different color. I don't know how well this will show up. Yeah, that blue is not really showing up very well. But my resultant vector is right here in blue. Okay? If again, say there was a collision. Maybe you have, one football player is traveling in this direction with this much force. Another football player is traveling in this direction with this much force. When they collide, the resultant force is going to kind of push both of them off to the right towards the angle 0. Now, one thing that's kind of interesting, when you add vectors together, and I think it especially kind of shows on a rectangular plot, if you were to connect all of the tails of these vectors together, you're always going to get a perfect parallelogram. Okay? This is something that always happens. In essence, like I said, if you could transfer this vector v up here to this dotted line, or if you could transfer this vector u down here to this dotted line, here you see you get this perfect parallelogram where this side is equal to this side and this side is equal to this side. And the resultant will always be right in the middle of that parallelogram. Here, 3, 0. All right, subtraction. We're not going to actually graph this one, but subtraction, I just want to show you a quick example. Super easy to subtract vectors. Here, if I have to subtract v minus u, and by the way, my u, v, and w are probably going to be different than the u, v, w you have on your assignment, but here all I'm going to do is I'm going to take 1 minus 2, which is negative 1. Take my 1 and my 2. And then I'm going to take negative 3 minus 3, which is negative 6. So just like you can add vectors, you can also subtract vectors. It's really easy. Just subtract your a's and then subtract your b's. All right, now let's look at an example with multiplication. So here I have this vector being multiplied by 2. This says take 2 times u, so 2 times 2, 3. And then plus 3 times w. 3 times negative 3, 0. Okay, well, let's start. The multiplication is really easy. It's just like distributive property. I'm going to actually, 2, 3, if you think about it, 2, 3 would fall right about here on my graph. You can imagine a vector kind of traveling this distance. Well, if I double that vector, all I have to do is multiply. It's like distributive property. I'm going to multiply both of these, the a value and the b value, by 2. Make this a 4 and a 6. 2, 3, 4. 1, 2, 3, 4, 5, 6. And look what happens. This original vector u, if I double it, turn the 2 and the 3 into a 4 and a 6, well, look what happens. The resultant vector just gets twice as large. It's still heading in that same angle, but it's just twice as large now. So this is 2u. Okay? And then 3w, I'm just going to take this like distributive property. I'm going to multiply both of these coordinates by 3. All right, and if the original vector was negative 3, comma 0, right here along the y-axis at 180 degrees, well, look what happens when I times it by 3. It's literally just going to make it 3 times larger. Now it's going to go out to negative 9, comma 0. This is the vector 3w. So right now in your brain, kind of just try to visualize right now. What would happen if I added this vector plus this vector? Even maybe kind of mentally in your head, like take this 3w and kind of mentally in your head transfer it up to the top here. Kind of mentally see what that would look like. Okay, my guess the resultant vector is probably going to be pointed out here up into quadrant 2. Well, let's add them together and see exactly what happens. If I do 4 plus negative 9, I get negative 5. If I do 6 plus 0, I get 6. So what's my answer? If I go to negative 5, 2, 3, 4, 5, and up to 6, 1, 2, 3, 4, 5, I was off by just a little bit. My resultant vector is actually right here. This is the resultant when we add 2u plus 3w. Okay, and yeah, let's say, here's a good example. Let's say you had kind of a tug of war going on. Two people were like fighting over a piece of gold or something like that, or gold necklace, I don't know. And one's pulling at this direction with this much force, and the other is pulling with this direction at this much force. What's going to happen is both of them are going to start traveling in this direction. This kind of tug of war is going to start pulling them at about right around 135 degrees. Notice also, you get this perfect parallelogram when you add these two vectors together. Okay, now as fun as all of that was really just a warm-up to what's going to be easily the hardest question on your upcoming quiz. And I think the hardest types of questions in this whole unit. How do we add two polar vectors together? So here it says graph u, graph v, then graph u plus v. Well, u is 3 and 45 degrees. A magnitude of 3 at an angle of 45 degrees. We can graph that real quick. Starting at the origin, if I head towards 45 degrees and I count out 3 circles, 1, 2, 3. Here on my graph, this is what u is going to look like. And then v is a magnitude of 2 with an angle of 165 degrees. So the coordinates are 2 and 165 degrees. So, 165 is on my little graph here. So this one's going to head towards 165 degrees with a force, a magnitude of just 2. So this is a much smaller vector here. So I start to imagine what would happen if I added these vectors together. And this one's going to be pointing close to 90 degrees, right? If I did the little head to tail method, I have one kind of going this, let me save that space. I have one kind of going this way. The other is kind of going this way. All right, if I add them together, it looks like it's going to go right at about 90 degrees. Well, guess what? You start to wonder, all right, well, Mr. Klein, how am I going to add two polar coordinates together? And I have some really, really bad news for you. The answer is you can't. You absolutely, positively cannot add two polar coordinates together. I guess if they were the exact same angle, you possibly could, or complete opposite angles, but otherwise, you absolutely cannot add these together. So the mistake a lot of students want to make, a lot of students want to just add these together and say, 3 plus 2 is 5, and 45 plus 165 is 210. And I wish it was that easy. But guess what? That doesn't work at all. There's no way you would add these two vectors together and get a resultant vector heading out here to 210 degrees. It doesn't work. Just flat out does not work. You can't find a resultant angle by adding together two angles together. It doesn't make any sense. So what do we have to do? What we're going to have to do is convert these polar coordinates to rectangular. And then add those rectangular vectors together. And then once we get that answer, we're going to have to convert it back to polar. See, here's a situation where, I don't know if you remember me telling you that triangles are everywhere in the physical world, and a lot of those triangles are invisible to the naked eye. In essence, the only way we can add these polar coordinates together is to turn each of these into a right triangle. Turn them into rectangular form, which is in essence turning it into, an opposite leg and an adjacent leg, turning this into like a little triangle, adding the horizontal components of the triangle together then adding the vertical components of that triangle together, and then reconverting your answer. That's exactly what's going on here. So these problems are tough, but let me walk you through it as best as I can. So here I have an r and a theta. The good news is going from polar to rectangular, super easy. Here I'm going to take 3 times the cosine of 45 degrees, comma 3 times the sine of 45 degrees. Okay, and let's do that conversion. And voila, since the angles were 45 degrees, these actually both came out the same. And I'd recommend, let's go out, our final answer, we're going to round to 1 decimal, but while we're working this out, let's go out to at least 2 decimal places while we work this out. All right, now let's convert this polar into rectangular. All we have to do here is 2 times the cosine of 165, comma 2 times the sine of 165. Let's calculate those. And here we go. Those add up. These convert to negative 1.93 and 0.52. And you can kind of check these answers. 2.12 and 2.12. If this were a rectangular grid, and I counted out a little bit past 2 on the x-axis and a little above 2 on the y-axis, yeah, I can absolutely see that falling where it does. Likewise, this having a negative 1.9 and a 0.5, I can imagine going roughly negative 2 to the left and up a half on the y. These answers make sense. And remember, these are really easy to add together now. So add these together, and boom, here is my answer as a rectangular coordinate. Okay. Now the thing is, though, I want my final answer to be polar. And so I'm going to write here, my last step, convert. So here I add them together. Convert back to polar. So for my last step, I have my A and my B. The magnitude of my vector, okay, the magnitude of u plus v is just going to be the square root of 0.19 squared plus 2.64 squared. I'm really just doing the Pythagorean theorem on this. Doing the Pythagorean theorem on this a value and this b value. Let's work that out. Okay, so I do the square root of a squared plus b squared. That comes out to approximately 2.6. It was actually like 2.647. I'm going to write 2.65 just to be safe. Okay, now let's find the angle. The way we find the directional angle is we take the inverse tangent of b over a, and I'm getting these formulas back from our last lesson. So if we do inverse tangent of 2.64 divided by 0.19, it does come out fairly close to 90 degrees. It's about 85.9 degrees. Now you do have to stop here for a second, remember, and figure out what quadrant this is in. Now since my A and my B are both positive values, that means this is in quadrant 1, and I don't have to make any changes. I don't have to add this by anything. I don't have to add by 180. I don't have to add by 360. So guess what? I have my final answer. The magnitude 2.65 at an angle of 85.9 degrees. So when I go to graph this, I'm going to look for an angle of 85.9 degrees That'd be roughly right about here. That's going to be close to the 90, not quite perfectly. And then from my origin, I'm going to extend out towards that at that angle, that mark, for a total of 2.65. If I add this vector plus this vector, I am left with this resultant. Okay? So that is my final answer. All right, man, these are going to be the trickiest ones. And let me show you one last thing off of your homework. All right, and this is question 11. And question 11 says we have to find 2b plus c. Okay, I want to talk first of all how to find 2b. To take 2, to multiply a polar coordinate by 2, the rule is you multiply the magnitude by 2, but you have to leave the angle alone. So here, you don't distribute. We're only going to do the 2 times 3 is 6. But then when you double the magnitude of a vector, the angle doesn't change. The angle's still going to be 330 degrees. So ultimately, 2b plus c, we're going to take the coordinates of 6 and 330 degrees, plus c, which is 2 and 90 degrees. Okay, and we're going to add these together. I'll give you one more little hint. I'll do the conversion for you. Let's convert this to rectangular. And here we go. I think the conversion from polar to rectangular really isn't that hard. This 6, 330 degrees converts to 5.20 comma negative 3. This 2 and 90 degrees converts to 0 comma 2. And so then you add these together. So here is the answer in rectangular coordinates. Okay, that's like my rectangular answer. Now what you have to do, convert back to polar. Take this answer now, convert it back to polar to be able to get your final answer. Okay, so I didn't give you the complete answer, but I hope that puts you well on your way. All right, hey, this was a long video, and this is a tough assignment. Best of luck on this. Be diligent on this. This takes some practice, but once you've practiced this a few times and get the hang of it, it actually has so many useful applications in the world of algebra and really in the world of physics and in the physical world. This shows up over and over again. All right, take care. Bye.